Hi, so my name is Maggie Emig, and the research I did over the summer was the absorption of greenhouse gases on magnesium oxide, and my research advisor was Michael Pierce. So the goals for our research were to determine how well greenhouse gases can absorb onto the surface of magnesium oxide. So what we wanted to do was prepare the samples ourselves and then put them into the vacuum chamber. And once they were inside the vacuum chamber, we would expose them to the various gases and we would anneal them and then analyze them. So we had two different samples, MgO001, which still showed pretty great lead patterns after the first and second exposure to methane gas, and then again after the exposure to CO2. We annealed it in vacuum, which left the surface very unordered, so we did not see any lead patterns at all. And then we annealed it in CO2, which did leave it with a lead pattern that was still fairly well, so we knew that it left the surface pretty organized. And for the MgO111, it had faint lead patterns after the methane exposures. The vacuum anneal left it completely unordered, so we didn't see any lead patterns at all. And then after the CO2 anneal, we did not see any lead patterns as well. So the first thing we did over the summer was we opened the vacuum chamber. In the picture, you can see the sample stage, which is what we used to rotate the samples to each of the instruments. And that is where all the samples that we have go. And we have to put samples in and out through a load lock, which allows us to raise and lower the pressure of the load lock instead of lowering the pressure of the entire chamber. And so the most important thing we had to worry about was checking for leaks and checking for fingerprints. If we had any leaks or fingerprints in the chamber, they would stop us from reaching our ideal vacuum, which is 1 × 10 to the -10 torr. Just to give you an idea, the atmospheric pressure is usually around 750 to 800 torr. So we had a pretty good vacuum. So this is our pump down data, and this is our gas analyzer. So the green line shows you all the contents that were inside the vacuum chamber the first day we started pumping down on it. And it just had a lot of contaminants, and the contaminants it had a pretty large quantity inside of the chamber. And the green line shows you what it pretty much looks like now. It has a lot less of the contaminants, and a lot of the peaks are different combinations of carbon molecules. So it can be, a lot of it is carbon, or we also have nitrogen, oxygen, water vapor, pretty much anything that is in the atmosphere is shown in the blue line. So these are about the samples. So the difference between the MgO001 and the MgO111 samples are that the 001 facing sample shows just one side of the unit cell, which for MgO is a square. So you can see on the figure that it would just follow the outline. So with any lead patterns, you would get a square or a diamond. For the 111 facing, you'd be looking at it on a diagonal, so you'd be looking at one of the corners and down through to the far other corner. So looking at it top down, you would see either a triangle or a hexagon pattern. So what did we do to prepare our samples? So we acid etched them using piranha solution, which completely gets rid of any organic substances that are on the surface. So this makes the surface very rough because of how strong of an acid it is. So in order to smooth the surface back out, we had to anneal the samples in a furnace for about an hour at 1100 degrees Celsius, and that left us with a very smooth atomic surface. And then before I get into the results of analyzing, these are the different types of analysis that we used. We used LEAD, which I had mentioned before, which is our low energy electron diffraction, and that shows us the atomic structure of the surface. And as I mentioned before, it shows us the triangle, the hexagon, or the square from the different samples. We had the AES, which is our Auger electron spectroscopy, which shows us the contents that are on the surface of our samples. And then the RGA data, which I had showed before, which is our residual gas analyzer, and it shows the contents of any gas that is inside of the chamber. So our first sample is the MgO001. The plot on the right shows a clean surface using AES, and the middle peak is our oxygen peak, and then we have our magnesium peak on the right. The peak on the left is a combination of different elements at low energy levels. A lot of elements have that lower level, those lower level peaks, so it just shows up as either a lot of little ones or as one giant peak. So this is a completely clean sample after we ion etched it, which is where we use an ion gun and we leak argon gas into the chamber, and the ion gun ionizes the argon gas, and the argon, since it doesn't want to bond with anything, it just pretty much clears away any contaminants that are on the surface. And just a sample naturally being in the vacuum chamber will pick up contaminants since we don't have a perfect vacuum system, but that is our way of cleaning off each sample. And we cleaned it off after each exposure to the gases, so we would start with a clean slate. So this is our MgO001 data after our second exposure to methane gas. The chart on the left shows the before and after the exposure, or immediately after the exposure, and you can see a very nice carbon peak on the orange line. And then we have our oxygen peaks, which didn't really change too much after our exposure. And then the graph on the right shows the amount of carbon after we changed some positions. It did show up pretty consistent, and we did end up changing the current that is going through the filament for AES. And if you have the current too high, it did end up knocking some of the carbon molecules off of the sample. So it was best that we kept it at a lower current, and then it stayed consistent no matter what position we were on. And we did find that the carbon did not decrease with time. So this is our data for the first exposure that we did to CO2. And just like before, we found that no matter where we moved, since our samples were 2 millimeters by 2 millimeters, we didn't have a lot of room to move. But when we did search the surface, we did find that the amount of carbon stayed the same. And each time we exposed it to the gases, we did it at around 1 torr for 10 minutes. And we found that that was a decent time to expose it and for the carbon and the oxygen to attach to the surface. So these are our lead patterns that I mentioned earlier. So the top two are how the sample looked when it entered the vacuum chamber after we ion etched it and cleared it of any remaining contaminants. And the smaller the dots, as seen in the top left picture, shows the better atomic surface. So the smaller the dots and the clearer compared to the background is the better surface. It didn't have as many interruptions, and it didn't have a disordered surface. As I had mentioned, like after the vacuum annealing, how it was completely ruined, so you wouldn't see any dots at all. And then the bottom two pictures shows the surface of our MgO001 sample after we exposed it to methane gas. So you can still see the pattern on the surface, which is great, but you can see that the dots were bigger and faded more, so it shows a little bit more of a disordered surface. So the picture in the top left shows how our sample looked after we annealed it in CO2 gas, and it showed a very nice lead pattern, even if the dots weren't super small like they were before. And the bottom two pictures are how our sample looked after we just normally exposed it to CO2 gas without the annealing, and they still showed very good lead patterns. The top right corner, that picture was taken by two other students a year or two prior, and it just shows the surface of an MgO001 sample, and it shows how they are more square And later I'll show a 111 sample, which will show a better triangle pattern. So this is our MgO 111 data after our second exposure to methane. And just like before, it showed a nice carbon peak, and we did find that when changing positions, it did leave a very smooth, even coating of carbon on the surface. And when we exposed it to the CO2 gas, just like before, it left a very equal layer of the carbon and an equal amount of CO2 on the surface. And here are our lead patterns. So as I had mentioned before, they do come out as triangles, and sometimes, like in the picture on the top right, you can see a grid of triangles or hexagons, and those were how they first were when it entered the chamber. So it shows very nice, small, concise dots, which shows a very good atomic surface. And we didn't quite know if it was because we etched it in piranha solution, which is not a typical acid that you would etch the magnesium oxide samples in, but we don't know if it was because of the piranha solution or if it was because we weren't wearing masks. If that made a difference, if the masks kept out more contaminants, which just left the surface smoother, or if it was the strong acid that we used. And the bottom two pictures were the samples after we had exposed it to the methane gas. So it was fuzzier, and I tried to pick energy levels that were close enough to really compare them and to show how it did get faded with the amount of gas that we exposed to it. And I just included the original pictures since we didn't get very clean lead samples from the CO2 exposure, or we didn't get any from the CO2 annealing. But the bottom picture is from the same students as before, and it does show the triangular surface of the MgO 111 sample. So just as a recap, the MgO 001 sample came out with better lead patterns after the exposure to methane and after the exposure to the CO2 gas, and the annealing for both did not work as well, though the CO2 annealing did work for the MgO 001 sample. The MgO 111 did not have as clean of lead patterns after the exposures, but it did seem to absorb more of the carbon than the MgO 001 sample. And the patterns did come out hazy and faded for the 111 samples. And the surface was just a little more disorganized than the 001 samples. And that is everything. Thank you for watching.